Okay, so we've made it to module 5, which is going to talk about double and triple integration. We are going to do double integrals over rectangular regions. All right. And so we again move from calculus 1 to calculus 2. We take and calculus 3. Calculus 2 gives us a whole bunch of integration, but calculus 3 and calculus 1 are very much alike, except that they are in different dimensions. Okay, so we want to learn how to compute what we call the double integral over R, f of x, y, dx, dy. Okay, so we clearly know how to integrate in one variable. So now what happens when I'm trying to integrate something like this? All right, well, let's go back to calculus 1. If f of x is greater than 0 on the interval AB, then the integral from A to B of f of x dx, that's simply the area of the region bounded by f of x on the top, the x-axis on the bottom, and a, x equals a, and x equals b. All right, so we know that's the area under the curve. So we had something like this. We had a function f of x, and we looked at that function from x equals a to x equals b. And in order to do this, we actually use what we call a Riemann sum. That means we split this little region up into pieces. So we split this region up into pieces, and then we took areas of these pieces. And we summed up these areas under the curve. Okay. So we looked at the areas of rectangles that were made by these pieces. Okay, so we have rectangles, and we summed up the areas, and we said as the n goes to infinity and the h goes to 0, the Riemann sum approaches the integral. Okay, so that's what we used. Okay, so now what we want to talk about is if we have f of x, y, and it's greater than 0, meaning it's above the xy plane, then the integral over the region on the xy plane of the function floating over top is just the volume d. So now what we have, okay, so now we have some region in the XY plane. So this is R down here. And then we have something floating over top. And so now we're capturing the volume that is underneath here. Okay, so whatever so now we're capturing the volume inside of here. So that's what we want to do. Okay. So we get the integral is defined in an analogous, hope I can spell it, way using upper sums and lower sums after having divided the region R into appropriate size rectangles. Okay, so that means that the same way I divided that region over there, I'm going to come over here and divide this region on the ground up into little rectangles as such. And then I'm going to find the area over top of the volume over top of each little rectangle square and then add them all up. Okay. How did you do that? Okay. Clearly, the simpler the region R, the easier it is to evaluate and to evaluate the integral and show it exists. Okay, so here's a simple one. Okay, before we even get into what we're trying to do, I'm going to do a nice simple one. Okay, so when I do the integral, so here's an example of what we're getting ourselves into. So I'm going to do the integral from 0 to 1 of the integral from -1 to 1 of x dy dx. Okay, so now what this says to me is integrating. So this says that y, you have to look at the inside piece. So here's the inside piece. So that inside piece says 1, I'm integrating with respect to y first. It also says -1 is less than or equal to y is less than or equal to 1, and it says 0 is less than or equal to x is less than or equal to 1. So I am actually integrating my region. So my region here turns out to be y goes from -1 to 1 and x goes from 0 to 1. So x goes from 0 to 1. And y goes from -1 to 1. So here is r. All right. Okay, any questions so far?
No, not right now.
Right. So when I go to integrate this, that means I'm going to do the inside first. So I have the integral from 0 to 1, and I'm actually going to compute the integral from -1 to 1 of x dy. Then after I get that, I will integrate that answer dx. My integral from 0 to 1. Now, inside, I'm integrating with respect to y. So that means x is a constant. So inside, I'm just getting x times y. And that is evaluated from 1 to -1. And I'm integrating that dx. So again, all of this is still on the inside. I get the integral from 0 to 1. When I put 1 in for y, I just get x. And when I put -1 in for y, I just get -x. So now this is the integral from 0 to 1 of 2x dx. That's x squared, evaluated from 0 to 1. And that's just x. So floating over top of this domain is the function f of x equals x. And it looks like a plank because x starts at 0 and it increases. And so therefore, that's what the function looks like. Okay, so now we want to talk about, so let's talk about a simple region. So for us, a simple region will be a rectangle. And on the rectangle are the set of all xy such that A is less than or equal to X is less than or equal to B, and C is less than or equal to Y is less than or equal to D. So this is some rectangle on the ground. And the volume V is the double integral over that region of the function of xy. And this is dx dy or dy dx. Either way, we're calling this thing dA. So dA can be dx dy, or it could be dy dx. It just depends on what I'm integrating first. So now I'm going to make a partition. All right, of A. I'm going to start it at x0, and then I'm going to have x1, and then I'm going to have x2. And I'm going to go all the way up to xn, which I'm calling B. And then I'm going to have a partition of y, which is y0 less than y1, less than y2. And I'm going to keep going all the way up to yn. And that's D. So now I have divided this region up into okay, so this little piece right here I'm going to call that piece dA because it's a delta X and it's a delta Y. Okay, so this is delta X and this is delta Y. So therefore dA, delta A is equal to dx times dy. And this thing is my partition P. Now, I'm going to make a selection. So the selection says on each square, choose 1 point. So my selection will be xi star, yi star on each xi, yi square. So that could be the point right there. It just is 1 on every square. And that is where I'm going to evaluate my function. So now my Riemann sum is just going to be the sum, I equal 1 to n, of f of xi star, yi star, and then I'm going to multiply by delta ai, which is the area of each square. Then we're going to let the norm or the area of the partition go to 0. So that's so that says that the smallest area, we're going to keep letting each little square go to 0. And when I do that, I get the limit as the norm of the partition goes to 0 of the sum, I equal 1 to n, of f of xi star, yi star, delta AI becomes the limit as n goes to infinity of the sum I equal 1 to n of f of xi star yi star delta ai. But if you remember from calculus, this thing in calculus 1, that thing becomes the integral. So this becomes the integral from a to b of f of x, y, d, a. Okay. So now we can find upper sums and lower sums. So upper sums and lower sums work the same way. Okay. So you can have a lower sum with the partition of f, and it's going to be less than or equal to the value of the integral. And if you remember, the upper sums are going to be bigger than the integral. Now, when you're on a square, okay, or a rectangle, it doesn't matter which order you do it in. So evaluation so evaluate double integrals on a rectangular region R. You have f of xy is continuous on R, and R is simply the interval AB crossed with the interval CD. So that's some rectangle. Then you get the double integral over the region of f of x dx, f of xy dA is the integral from a to b of the integral from c to d of f of xy dy, then integrate that dx. And that's the same as the integral from c to d. And we do the integral from a to b of f of xy dx. And do that first. And then we do dy. Okay. And this is called an iterated integral. Okay. Here's an example. I want to do the double integral over R of y minus 2x dx dy, and R is equal to the set of all xy such that 1 less than or equal to x less than or equal to 2, and 3 less than or equal to y less than or equal to 5. So that's some block of some square, like a placemat on the ground. And then this function f of xy is floating over top. So you have z equal to y minus 2x over top. So that's just a plane. Okay. All right, so we get the double integral over r of y minus 2x dx dy. So it says dx dy, so we got y on the outside. And on the inside, I have the integral from 1 to 2 of y minus 2x dx. I'm going to do that first, dy. Okay. So this is the integral from 3 to 5. When I compute that integral and I'm integrating with respect to y, with respect to x, I'm going to get x times y minus x squared. Evaluate it from 1 to 2, and then the rest I'm integrating dy. So as you can see, I integrated y came from xy, because this is the partial with respect to x, so I integrate that, and then the x integrates back to x squared. So this gives me integral from 3 to 5. On the inside here, I put in a 2 for x. So I get 2y minus 4. And then I'm going to subtract, and I'm going to get y minus 1. Now I'm integrating that dy. So now I get the integral from 3 to 5. I have 2y minus y gives me 3y. I have negative 4 minus a negative 1. That gives me negative 3. How did I get 3y? I got 2y minus 1y. That's y minus 3. Okay. So that becomes 1/2 y squared minus 3y, evaluated between 3 and 5. So I'm going to get 25 halves minus 15 minus 9 halves minus 9. So 25 halves minus 9 halves is 16 halves, so that's 8. And then negative 15 minus a negative 9 is minus 6. So my answer is 2. Okay. Anaya?
Yes.
All right, you're going to do the other direction. Y minus 2x. You're going to do, what did I just do? I did dx dy, so you're going to do dy dx. So you are going to do the integral of x goes from 1 to 2 And then you're going to get y, forgot my integral. The integral from 3 to 5 of y minus 2x dy gx. Okay, let's go. What do you do?
Sorry. So don't you have to integrate it first? Find the integration of y
You got-
minus 2x.
Right, so you got to integrate that with respect to y. So when you integrate that with respect to y, what do you get?
1/2 y squared
Okay, good.
minus 2xy.
Minus 2xy. This girl is on it. Oh, I love working with Anaya. Ooh. Okay. She learned something. She knows her stuff. Okay, so what do we do next?
Didn't you plug it in or did not yet?
Right, so we have to evaluate we have to evaluate this using the fundamental theorem of calculus. So you got to put in a 5 and then you got to put in a 3. So what do you end up with?
So 25 over 2, 12.5.
25 over 2.
And then that's, I have to put in a 5.
Or y
Yeah, okay. Minus 10x.
minus 10x.
And then the 3 one would be 9 over 2 minus 6y. I mean 6x.
Okay.
And then
All right.
when you subtract them, it would be 16 over 2, which is 8, plus negative 4, well, minus 4x.
Okay, keep going.
And then you put the 2 in for the x.
You got to integrate that first.
Oh, let me see. 8x, well, is it still according to y?
8x. No. Y's are gone. Now the only thing
Oh,
left
okay.
is x. You see, you have dx on this side. No
Mm-hmm.
more y. So 8x. Go ahead.
Minus 2x squared.
2x squared. Evaluate it from 1 to 2.
Okay, so it'll be 16 minus 8. And then it'll be 8 minus 2. So 8 minus 6 is 2.
Yay. Okay, so we better get the same answer.
Mm-hmm.
Okay. All right. Now what happens? So that's easy. If it's a square region or a rectangular region and it doesn't have any X's or Y's in the region, then you just go ahead and do it. Okay, so now what happens when we have general regions? Okay. Okay. All right, double integrals over general regions. Okay. I'm behind in my other class, both classes. Whew. They're stressful. I can't rush the material because I can't do that to my students.
Mm.
So we have a bounded, so we have a bounded region R. Okay, so my bounded region R looks like this. And again, I go through. So my region R is bounded. So maybe it looks like this. But I can fit it inside that box. Okay, so it's bounded. So I'm gonna do the same thing again. I'm gonna take and partition this region. Okay, all righty. So now we know that we can do an inner partition, all right, on all the rectangles inside the region R. So the region R, let me. So this is R. And I can construct an inner partition okay, on all the rectangles that are inside R. All right, so P is the partition. All right. Then again, we're going to define this to be the mesh of P. And again, we're going to get a selection. Set of xi star times yi star on each for each rectangle. Okay, and then we're going to get a Riemann sum. So that's going to be the sum I equal 1 to n of f of xi star yi star delta a I. Okay. And so now we're going to let the norm of the partition go to 0. All right. And so again, we get the same thing. Double integral over R of f of x, y, d, a is the limit as n goes to infinity of the sum I equal 1 to n of f of xi star yi star delta xi of delta ai. All right, so now we're going to have a definition. And so this time, this is the definition of the double integral. Okay, so we're going to have a plane region R. And this is a general region. All right. And I is equal to the double integral over R of f of xy dA if for all epsilon greater than 0, there exists a delta greater than 0 such that for all partitions P, such that the norm of P goes to 0, we can show that the absolute value of the sum I equal 1 to n of f of xi star yi star delta ai minus I is less than epsilon. Okay. So now I want to talk about simple regions. Okay. This is a lot, so I'm going to type it. My hand gets tired. I need to type. Okay. Number 1, a region R is vertically simple if there exists functions g1 of x and g2 of x that are continuous on AB such that g1 of x is less than or equal to g2 of x for all x in the interval AB. Okay. Okay. A region R is horizontally simple if there exists functions I'm going to call these H1 of Y and H2 of Y that are continuous on AB, CD, such that H1 of Y is less than or equal to H2 of Y for all Y in CD. This time change has me dragging in the evening.
I agree.
Yeah, it is hard on me. Okay. A region R is just plain simple if it is both horizontally and vertically simple. Okay, this is easy to draw. Okay. All right, so this one is G2 of X. This one is G1 of X. And between A and B, so on that whole interval, okay, on that whole interval, G of X is bigger than H of X, okay? Okay. So now I have H1 and I have H2. And then I'm going to choose a C and a D. Okay, so this is H1 of Y. Over here is H2 of Y. I forgot to put in here, this is A and this is B. I want to put in this is C and this is D. So it's simple. As you can see, it's horizontally simple. That means I'm always going from one function to the other function. So I'm always going from one function to the other function. Here, I'm always going from the bottom function to the top function. Okay, and then the last case is a very interesting case, because this case it's just plain simple. And that generally looks like something like this. Okay, so now as you can see, I'm always starting from one function. I'm always starting from one function and going to the other function, or I'm starting from one function and going to the other function. Okay. All right, so this one, the first one is vertically simple. The second one is horizontally simple. And the last one is just plain simple. Okay, so now this is where life can get difficult. So now let's look at our iterated integral now. Okay. We have f of xy. Again, is continuous on my region R. Okay. So for if it's vertically simple, so if it's vertically simple, that means I have a function. I can say that y always goes from g1 of x to g2 of x. Can you see that? In this one, the y value always goes from g1 to g2. And in the horizontal one, it always goes from h1 to h2.
Okay.
When it is vertically simple, we say v equal to the volume, equal to the double integral over r of f of xy dA is the integral from a to b. So you have to do the inside first. And on the inside, let me not do that. That's confusing. So we're going to go from g1 of x to g2 of x, f of xy dy, and then everywhere you see a y, you will put in the functions of x that you get, and then you will integrate that dx. And if it is horizontally simple, you would get the volume being the double integral over r of f of xy dA is equal to the integral from c to d. And now inside, you're going to do the integral from h1 of y to h2 of y. You'll integrate your function f of xy dx. And then after you compute that, you will integrate the results dy. Okay. So
I think you wrote it wrong.
I did. Thank you. That means you know what's going on. When you can pick my errors out, that means you know what's going on. I love it. So here's an example. We're going to compute it one way, and then when we come back on Monday, we will compute it the other way. Okay? So we're going to compute in two different ways. Because this region is simple. So that means I can compute it in two different ways. The double integral over the region R of xy squared dA, and R is the first quadrant region bounded by y is equal to the square root of x. and y is equal to x cubed. Now, it turns out this region is, like I said, simple. So we're going to first do it in terms of being vertically simple, because that's the way it was given to us. We may as well do that. So here is y is equal to the square root of x. And then the bottom curve is y is equal to x cubed. Okay, so now I'm looking at this and I can see that this thing is vertically simple. Okay. That's not what I want to do. Let's just scratch that. Let's do it is horizontally simple first. No, I think I did it right the first time. That's what I want to do. It is vertically simple. Okay. So now I get the double integral over r of xy squared dA. Okay, well, what do I do? What do I do? What do I do? Okay, so I can clearly see that y starts at x cubed and it ends at the square root of x. Do you see that?
Yes.
Okay, so y starts. So now the question is, where does x go from? Well, this line can start way over here at x equals 0. And that line can keep going till it gets way over here. And so we need to find this value of x. So that value of x is where x cubed and the square root of x actually meet each other. So I get x cubed minus x to the 1/2 is equal to 0. So factor out x to the 1/2. I get x to the 5/2 minus 1 is equal to 0. So I get x is equal to 0 and 1. So therefore, this value is 1. So x goes between 0 and 1. So now I get the double integral over the region of xy squared dA is the integral. X goes from 0 to 1 and y goes from x cubed to the square root of x, and I get xy squared. I'm going to integrate with respect to y first, and then I'm going to integrate with respect to x. Okay. So now, when I go to do that, I get the integral from 0 to 1, and on the inside, I'm going to integrate with respect to y. So I'm going to get 1/3 x y cubed evaluated from x cubed to the square root of x, or x to the 1/2 power. And that's what I'm going to integrate dx. So this is the integral from 0 to 1 When I put in x to the 1/2, I get 1/3 x times x to the 3/2 power. And then I'm going to get minus 1/3 x times x to the 9th power. So I'm now integrating the integral from 0 to 1. I'm going to pull the 1/3 out because I don't need it. So now I'm going to get x to the 5/2 minus x to the 10th dx. So now I get 1/3 x to the 7/2, and I'm going to get 2/7 minus x to the 11th. I'm going to get 1/11. Evaluate between 0 and 1. So I get 1/3, 2/7 minus 1/11. And when I put in 0, I'm gone. Okay, so that's 1/3. I'm going to get 22 minus 7/77. Is that what I got before? Yes, and 22 minus 7 is 15, and 15/3 is 5. So that's what I get. So on Monday, we will compute the other direction.
Okay.
Okay. Thank you, my dear. Appreciate it.
Of course. See
All
you
righty.
Monday.
Okay.